Okay, let's do one more frames problem and get through these. Okay, so this is a little slightly different setup than we've been seeing. But in this case, this question asks to find the reaction on the members at A, at D for member DE, and at B for member BD, right? So we've got these three sections of a beam that are supported by rollers fixed at A and then connected at pins, right? Okay, so let's go through this. So again, pause the video and think about what you're going to do. Try and solve it, and then come back and use the video to troubleshoot. So let's go ahead and draw a free body diagram of the whole thing so we can understand what's happening, and then we can start taking it apart. So here we're going to do a free body diagram of the whole thing, member AE. Make sure you're good with all the supports here. So at A, we have a fixed support. That means we're going to have three reactions, AY, AX, and the moment. At A, we have 9 kilonewtons external. We have C, CY, and at E, we have a roller at EY. And we have this 10 kilonewtons over here on this side. And we have a moment applied. It's a little bit complicated. 10 kilonewton meters. Hopefully you can see right away using this free body diagram, you at least get one freebie, right? Which one is that? Sum of forces X. Let's draw a coordinate system. Sum of forces X, positive forward, will tell us that there's nothing happening in the X direction. AX equals 0. So that's the easy one. But now, of course, we still need to know AY, MA, whatever's happening at B, so we'll need to take this apart. So let's start there. So free body diagram of AB. Again, at point A, point B, AY, AX, which we already know is 0, the moment, MA. And now what's happening at B, right, for this one? We've got a pin connection at B, so there's going to be BY, BX, and we have the 9 kilonewtons, and that's actually right in the middle. So we can use this one at least to solve for what? AY, and, oh, maybe not yet. Let's see what happens. I'm thinking this is not going to be so good, right? We could take the sum of moments at A, but if we do that, we're still going to have MA in our equation, and BY in our equation are going to be unknowns. If we take the sum of moments at B, right, we know that's going to be a function of MA again and AY. So now we're three unknowns. And then if we do sum of forces X, all that tells us is that BX is equal to 0, so at least that's not an unknown. And if we do sum of forces Y, then sum of forces Y is going to be a function of AY and BY as well as the other knowns. So this is getting kind of complicated, right? It's a lot of work. You have three equations, three unknowns. You're going to have to solve for that linear system of equations. Not terribly difficult, but maybe a bit more time consuming. So let's take a look at another section, right? This section is only going to get us the answer we need for A, Y, and MA. But the question asks for the reaction at B in member BD, right? So these would be equal and opposite to whatever we want. Still useful, but maybe there's another way. So let's do a free body diagram of section BD. where we don't have to solve so many equations simultaneously. Okay, so we'll draw another coordinate system. So now we're going to be right in the middle, BD. And now that you've sectioned this, what you want to make sure is that you're drawing your reactions opposite to the one above, right? Because now these are the reactions on member BD, which should be equal and opposite to the reactions at B from member AB. So now I'm going to draw BY coming down, and then I get to pick arbitrarily dx and dy. Oops, dy and dx. And then we have cy right in the middle, yes. And we have that external 10 kilonewtons. Now we already know Bx is equal to 0. Sum of forces x will tell us that dy is equal to 0. But still we have 1, 2, 3 unknowns. So another section that we can work with that's going to be a little bit easier. We need the forces at members in member D at DE anyway. So let's do DE and see what that gets us. Right, here we'd be in the same boat. If I went back to the example above, I'd have to do sum of moments at B, so I could have something that's a function of cy and dy. Sorry, this should be x. Then I'd have to do sum of moments at D, so it's again a function of by and cy. It's at least just two equations, but I still have to solve for them simultaneously. We're all about efficiency, so let's see if we can find another place that gets us answers directly that we need. So let's do DE. So here E, D, again being consistent, right, with the sign. So dx needs to now point to the left in order to balance what was happening up here. Right here. And then to balance this dy, I'm going to draw the next one with the dy coming down. I have the 10 kilonewtons in the middle, and at E I have EY coming up. So now I can take the sum of moments at D and get EY straight away. Positive counterclockwise. So we have EY, and I'm going to call these 1.5 meters A. So let's call these distances. Fortunately for us, they're all the same. So this is A, this is A. So EY times 2A minus the 10 kilonewtons times A equals 0. EY equals 5 kilonewtons. Not a result we actually care about in terms of solving the problem, but now we can really easily do sum of forces y, EY minus dy minus the 10 kilonewtons equals 0. So we can see pretty straightforward that dy is equal to minus 5 kilonewtons. Now be careful here. Right? What direction is dy pointing in right now based on my sign convention? It's pointing down, right? But I'm finding that it's a negative answer. So that means that direction is wrong. So be careful. The magnitude is correct, always, right? It's going to be 5, but the sign is wrong. This should be is a positive answer because the question said, what is the reaction on D for member DE? This is the reaction that I care about on member DE, and it needs to actually point in the other way, right? So when you put this into Prairie Learn, when you answer the question here, dx, of course, is going to be equal to 0, and dy, in terms of a force vector, is going to equal a positive 5 kilonewtons in the y direction, j hat. Okay, so now that we've got that one, we can come back up and start figuring out the rest. So we've got dx and we've got dy. And the question asked for what else is happening at member B. Now we can come grab this free body diagram and start solving for these now that we have a few more knowns. So now that I know what's happening at D, I can take the sum of moments, right? Sum of moments at C, maybe. Positive counterclockwise. That'll give me the unknown that I care about. We already know Bx is equal to 0. We still want to know what By is. So this dy, I still put in minus 5 kilonewtons. Right? I'm not going to change this arrow because of the previous answer. I'll leave those alone, but I just substitute in the correct magnitude that I found from before. So I always do forces in red. Minus 5 kilonewtons. Okay, so that's going to be a positive moment, minus 5 kilonewtons, times the moment arm A, plus By times its moment arm A, minus the 10 kilonewtons. Whoops, getting a bit messy here. Minus 10 kilonewtons meters equals 0. So now I can solve for By right away. If this is confusing how I'm getting these negatives and the signs of the moments, let's do this symbolically and then plug in after. So I'm going to do this again. So this arrow is pointing up, right? That's the sign convention that we've decided on. That's how we set up all these free body diagrams. This is going to be a positive moment, dy times A. By is also positive, plus By times A. Right? Oh, I'm supposed to do this in purple. Anyway, minus 10 kilonewton meters equals 0. Now I'm just going to substitute in, right? Let's go ahead and solve for this in terms of the By. So By times A is equal to 10 kilonewton meters minus whatever dy times A is. So By A is equal to 10 kilonewton meters minus, and we found that dy is equal to minus 5 kilonewtons times A. So hopefully that's clear. By A is equal to 17.5 kilonewton meters, and now By is equal to 11.6 kilonewtons if A is equal to 1.5. So now what does that mean? By is 11.6 kilonewtons. So again, watch the signs. The magnitude is correct. The sign is correct for By. But what direction is By pointing in? By is negative 11.6 kilonewtons J hat. Okay? So just watch those signs when you're getting those done. Okay, so that's B. And then the last thing we need, now that we have B, is to come all the way back to the free body diagram here. We know By, Bx, and now we can go ahead and solve for A and the moment at A. So this is, again, the answer you put into PrairieLearn. Here's the answer you solve into immediately in terms of these signs. So now we know By, we know Bx. Now we can go ahead and solve, right? So let's do sum of forces y to get our unknown Ay. So Ay plus By minus 9 kilonewtons equals 0. Ay equals 9 kilonewtons minus the By. Ay is equal to 9 kilonewtons minus, I found that it was 11.6 kilonewtons, right? So Ay is equal to minus 2.6 kilonewtons. So what does that mean? Again, the magnitude is correct, but the sign is going in the wrong way. Ay should actually be pointing down. And so that means this will be a negative, right? So we're already there here. So the magnitude is correct. The sign is wrong in terms of this arrow here. This arrow should be pointing down. And so when you put it into PrairieLearn, you should be getting Ay is equal to a minus 2.6 j hat. And last one is sum of moments at A. So we'll do this symbolically, by times 2A plus the ma. Now that we know everything else, we can go ahead and solve for this. Minus 9 kilonewtons times A equals 0. Once you plug everything in, you're going to find that the moment at A is equal to minus 21.5 kilonewton meter. That means it's a negative moment. It's a clockwise moment, which for this coordinate system would be a negative answer. And that's how you solve this problem. So there's moment at A, AY, BY, the BX's are all 0, and then the DY here. Okay, that's it.